In this video, I'll present our paper, Ferret, Fast Extension for Correlated OT with Small Communication. This is a joint work with Yang Kang, Lan Xiao, Zhang Jiang, and Wang Xiao. First, let's take a look at the functionality of Correlated Oblivious Transfer, or the COT. The COT functionality generates correlated messages for the sender and the receiver. As we can see in this figure, the sender inputs a global delta. The functionality outputs V to sender and UW to the receiver. The U consists of the choice bits. The V and W are correlated by the global delta. It is a powerful primitive and has many applications. First, we can use the COT to generate other variations of OTs like standard OT and random OT. Also, it is widely used in secure multi-party computation protocols to achieve semi-honest and malicious security. You can also see it in circuit-based zero-knowledge proof protocols and some specific protocols like private set intersection or threshold signatures. In this paper, overall, we design a protocol that efficiently generates correlated OT and achieves security against the semi-honest and malicious adversaries. Our scheme is based on learning parity with noise assumption. We also open sourced our implementation. It has the property of both low communication and low computational overhead. Specifically, we use the vector oblivious linear evaluation based on LPN assumptions to generate the correlated messages. There are some prior works following this line of research. They were able to achieve high communication efficiency or high computational efficiency, but not both. For example, the Boyle et al.'s paper is based on dual LPN assumption. It has an amazingly low communication overhead, but the computation is too complicated. The Shulman et al.'s protocol is based on primal LPN assumption. It requires more communication but allows cheap local computation. Let's take a look at how COT is generated based on these two LPN assumptions. The primal LPN assumption can be viewed as the standard LPN assumption. It takes a public matrix A, a random vector U, a noise vector E. E is a sparse noise vector with fixed Hamming weight. The primal LPN assumption states that when we multiply public matrix with the random vector U and add a layer of noise, the result is indistinguishable from a random vector B. If we view this U vector as a seed, we kind of expand it to be a pseudo-random string, and it is indistinguishable from a random string. We can use this property to expand a small number of COTs into a large amount of COTs. Here are the specific steps to generate a vector of n COTs. First, we obtain k COTs with choice vector u. This is the seed we want to expand, and the k is much smaller than n. The sender has v and delta, the receiver receives the u and w. Then we obtain n COTs with choice vector e. E is supposed to be a sparse noise vector. There is a much more efficient way to generate it with only log n communication cost. Now the sender has the s and the receiver has vector e and r. Then they combine what they've got on first two steps based on LPN assumption. They expand the k COTs into n COTs by multiplying it with the public matrix A and add the noise vector of length n that they obtained at the second step. Then two parties get the COTs of length n. The computation is cheap, but the communication is non-trivial to generate k input COTs, but we'll solve this problem later. The dual LPN assumption is a variation of the standard LPN assumption. It states that if we use a matrix to compress a sparse noise vector, the output vector is indistinguishable from a random vector B. We can use this property to compress a large number of COTs which has sparse choice vector to a short random COT vector. It has cheap communication only proportional to the Hamming weight of this sparse vector, but it requires heavier computation, including the FFT operations. Now a question left is how to efficiently generate a COT with a sparse choice vector. An important building block is the single-point correlated OT, or SPCOT. The goal of SPCOT is for the receiver's choice bit to be 1 at only one position and 0 at the rest. It means that the sender and the receiver's COT messages are identical except at one position, where they have the shares of the global delta. It can be efficiently achieved by a Markov tree structure. The sender uses a COT to share the nodes of the trees. At last, the output COT messages are the leaves of the Markov tree. It only requires the local-end communication. Using the SPCOT, the parties generate the sparse noise vector for the VOLE. Based on these previous works, we design a new protocol that's based on VOLE and a primal LPN assumption, which is secure against malicious adversaries and has low communication and computational overhead. When we use the regular noise for the noise vector, we manage to achieve around 20 nanoseconds per COT even in low network bandwidth. We further optimized our code after the paper being submitted. Now we can sure to achieve lower than 17 nanoseconds per COT in most network settings. There are two key ideas that are included in our optimizations. The first key idea is the iteration. As we can see from the LPN assumption, first we need a small number of COTs as the seed, then we expand it. At the very beginning of our protocol, in the one-time setup phase, we first generate a small number of COTs using the IKMP style of the extension. Using these COTs as inputs, we run our COT protocol based on LPN assumption with a small set of parameters to expand more COTs. This serves as the input of the main protocol. One part is the seed vector U. Another part will be used to generate the noise vector E. After the execution of the main protocol, we preserve a small number of COTs as the input of the next iteration. Because most of the communication overhead in prior approaches are from the generation of input OT, it can significantly reduce the communication and accelerate the execution. The second key idea is to achieve the security against the malicious adversary by a fast consistency check. The prior approach for malicious security requires 2 times of calls to the PRG compared to semi-honest security case, and it has to hash a long string. Our approach uses a linear combination to achieve malicious security. Now the sender has vector V and the receiver has vector W. The length is n and they are identical except in one position alpha. We can assign a random coefficient to each element and use the linear combination of the elements to check the consistency. The left side can be computed locally and the shares of right side can be computed by a small number of input COTs. The consistency check can also be batched when multiple instances are executed. These operations, especially the multiplication in the 2 to the k field, are efficient using the hardware support, and this check has a low communication cost. Overall, our protocol is more efficient than previous approaches. We have a low communication, and it runs fast in both low and high network settings. And these are the setup times if we generate 10 million COTs. Even if we count this time in, the end-to-end performance is still very good. And we also support LPN with uniform noise and have done some optimizations on previous works. But due to high computational costs, there will be some performance penalties. This work can be a foundation of many other works. As we have seen at the beginning, the correlation generation like COT has many applications. Following this work, we design a subfield VOLE based on prime field. We generate a correlated share for only 87 nanoseconds, when the network is 50 megabits per second. Using the binary field and prime field VOLEs, we also design ZK protocols of Boolean and arithmetic circuits. The VOLE correlations can be used to generate information theoretical max for each wire in the circuit, and also be used to generate pre-processing triples for the consistency check. Based on the subfield VOLE, this protocol can be really efficient. At last, there is a link to the full version of our paper. You can also check our code in the EMP library. Thank you.